Ranjan from Department of Materials Engineering in Institute of Science, Bangalore. First of all, I'd like to thank the Indian Academy of Sciences for the invitation and giving me an opportunity to share some of the interesting works we have carried out in the recent past. My main area of research, as mentioned by this, is ferroelectric materials. The emphasis here would be, I will just try to showcase some of the interesting results which I have discovered in the recent past in our group. As is most familiar to many people, is a phenomena where when you electric field and switch the electric field from positive to negative direction, the polarization also switches, resulting in a hysteresis loop called PE hysteresis loop. Now, the shape of this hysteresis loop is more or less similar to what we have seen in ferromagnetic materials in terms of magnetization as a function of magnetic field. This historically led to the name ferroelectricity, though there is no ferro means iron, there is no iron in most of the ferroelectric materials which I will talk about. The condition for a material to be ferroelectric is intimately related to its crystal structure. A ferroelectric material necessarily should have a polar symmetry axis from the point group point of view, and it so happens that of the 32 point groups, crystallographic point groups, only 10 exhibits this feature. This diagram shows this is a ferroelectric material at the unit cell level, and it has a net polarization P vector. Now, the polarization will be able to switch. That is the most important requirement for a material to be ferroelectric. If it doesn't switch, then the material is not a ferroelectric. It can be termed as a pyroelectric, which has its own important significance. Now, the switching of the polarization is made possible because there are domains which are mobile. So often when we see domains in ferroelectric materials like this one, we see one polarization here, another polarization in another direction, divided by a boundary called domain wall. Now the presence of these domain walls comes from the fact that the system likes to minimize its electrostatic and elastostatic energies because of the development of polarization. There is some this is electrostatic requirement where you have a divergence of P related to divergence of E, and the direction is negative. To minimize this depolarization field because of this sudden abrupt truncation of the polarization at the surfaces, you get this depolarization energy, which add cost to the total energy of the system, and the system tries to minimize this energy by forming domains in different directions and a consequent domain wall. The domain wall should be mobile. This is the most important feature. If they are not mobile, set to ferroelectrics. Now, it was the ferroelectric phenomena was discovered long ago, and the ferroelectrics has been used in wide-ranging application, like in capacitor industry and electromechanical devices, which I'll be talking about today. And though the field is very old, it continues to reinvent and develop thanks to the discovery of novel materials and new related phenomena related to ferroelectricity from time to time. Here I am trying to show some of these examples, like this is a coupling of polarization to the strain leads to electromechanical effect, which I'll be discussing about in a detail in today's step. Also, ferroelectric materials are used in memory devices, like this is a ferroelectric random access memory. And also this memory has also been used in more recently via tunnel barrier heights. The polarization affects Schottky barrier across ferroelectric metal junctions, and which we can manipulate to design new tunnel-based memory devices. Ferroelectric materials are also used in infrared sensors via the pyroelectric effect. More recently, in the last 2 decades, there has been increasing interest in other coupling of ferroelectricity, like a coupling of light with ferroelectricity, leading to the field like photoferroelectricity, Some interesting phenomena associated with this is photocatalysis and photovoltaic effect. The intrinsic polarization which has corresponding electric field, when you shine light on this, the electron hole pairs which get separated by this internal electric field, which is the equivalent to the p-n junction in conventional semiconductor, where the intrinsic electric field at the junction pulls the electron hole pair apart with the current. Also, ferroelectricity has seen very interesting application recently in electrocaloric devices. We have magnetocaloric devices which has been known for quite a long time, but analogous effect in electrocaloric devices are also being investigated seriously, because if you have such a devices, not only it's cost effective in terms of energy, but also it's quite miniaturized. Also, the phenomena of ferroelectricity and magnetism coupled together has led to the field of something called magnetoelectricity in the recent past. That this year is the centenary year of the discovery of ferroelectricity. It was discovered in 1921 by J. Walazek in single crystal of Rochelle salt, which is a water-soluble compound. So, but a great breakthrough happened during the Second World War with the discovery of ferroelectricity in oxide material, like this ferroelectric AbO3 perovskite type material. It was discovered in a compound called barium titanate. Now this is a ceramic as compared to the previous Rochelle salt and other water-soluble compound. Ceramic has the benefit that it will not dissolve in water definitely, and it is more rugged and strong. A typical structure of ceramic is like it has lot of grains which are bonded together. You can make it in shape as you wish. It's quite cost effective in fabricating, and the discovery of piezoelectricity in ceramics led to revolutionize the field. In terms of that, one can make low cost piezo ceramics, because ceramics are easy to fabricate in wide ranging shapes and sizes as per our convenience. The most widespread use of ferroelectric material, as I said, is in the electromechanical devices via the piezoelectric effect. There are two kinds of piezoelectric effect. One is called direct, another is called the converse piezoelectric effect. The direct piezoelectric effect phenomena is that when we stress the material, it develops polarization or the voltage, and the converse piezoelectric effect is that when you apply electric field or voltage to the material, it develops strain. Now, these are the two fundamental phenomena which has been exploited in wide-ranging applications in piezoelectric or electromechanical devices. The coefficient D is called the piezo. It's a figure, one of the important figure of merit. It's called the piezoelectric coefficient. And for a piezoelectric ceramics, there are basically three different type of coefficients: D31, D33, and D15. The most widely used piezoelectric ceramic material is called PZT. It's an alloy of lead zirconate and lead titanate. It's basically a solid solution. And however, because of the increasing environmental concern all over the world, there is, in the last 2 decades, has witnessed an increasing focus on developing lead-free alternative of PZT. This slide shows where the piezoelectric market stands in terms of economic activity. It presently has 25.1 billion market share, still growing at 6.2% rate annually. And with the lead-free piezoelectric ceramics also picking up, and it's growing at a very much faster as 20.8%. And it's predicted that it will be, by 2024, the market share will be quite large for this lead-free piezo ceramics as well. Now, I'll be focusing here with some of the ferroelectric research which we have been carrying out at IISc. Our focus primarily, mostly remains on the actuator side, developing material for actuator, understanding the mechanism behind that. Also, we have also delved on some other related phenomena like multiferroic, where there's a coupling of polarization with magnetic field. Also, we have investigated recently something called photoferroelectric phenomena, where we try to uh, uh, manipulate the light coming out of the ferroelectric material by electric field and play with temperature, etc., and think of making new devices. The high performance piezoelectric actuator materials are basically among the oxide called perovskite, come from perovskite family. They are not compounds, but they are rather solid solution. PZT I have already said about, but now also we have seen in the last 2 decades many interesting ferroelectric solid solutions of these perovskites showing large piezoelectric effect. Now, looking at the phenomenology, if you look at the phase diagram of any one of these, like this PZT, which is a lead zirconate and lead titanate, the phase diagram shows a line called morphotropic phase boundary, which separates two different ferroelectric crystal structures. So basically, this is a composition and temperature-induced interferoelectric instability. So, for example, here you have a tetragonal phase with the polarization along the c-axis, and on the other side you have a rhombohedral phase with the polarization along body diagonal of that unit cell, you can see. So at the phase boundary there is an instability which leads to the system becoming more highly susceptible to electric and stress fields. Now, one of the characteristic features of this phase boundary, which we can easily see as an experimentalist, is it comprises of coexistence of both the phases, rhomboidal and tetragonal phases, seen by analyzed using X-ray diffraction. As this figure shows, the electromechanical response is enhanced when you have a composition close to the phase boundary, generally called morphotropic phase boundary. Large electromechanicals that is one part. The interferoelectric instability leads to the instability in the polarization, which you can easily turn when you apply electric field. That leads to large electromechanical response. The other part is the domains themselves contribute significantly to the large electromechanical response. Because there are more number of domains at this boundary and they are more mobile, and that contributes to the large electromechanical response. Now, as contrast to this scenario, we have recently discovered that you need not have a morphotropic phase boundary, but still can get large electromechanical response. We have investigated 3 systems in the recent past. One of this system shows an extraordinary electrostrain of 1% in a polycrystalline piezoceramics. To understand the significance of this 1%, why it is extraordinary, because you can see the other one, which the previous reports which shows a strain was about 0.7% in a ceramic, that was in 2015. And so 1.3% is almost twice of what we have seen in the previous case. And this is, if you can look at the traditional PZT, it's almost 3 times what is traditional PZT shows of the electrostrain, which is about 0.3 to 0.4%. So that's why it was extraordinary. When coming to the mechanism aspect, we found that it is not really the morphotropic phase boundary, that there is interferoelectric instability which leads to this phenomena. For example, that we look at the XRD pattern of this, we found that the composition which shows the highest electrostrain is a mixture of cubic plus tetragonal phase, not cubic plus rhomboidal, which usually the MPV comprise of. What is most interesting is that once you apply strong electric field, this cubic phase is completely suppressed, almost suppressed. A little bit of it, which has a very important role to play, which I'll explain in the next slide. So the phase diagram of this material is called bismuth ferrite lead titanate with some lanthanum dissolved in it. So this is the phase diagram of lanthanum concentration. It also shows tetragonal, but instead of a rhomboidal, which is typical of MPV, morphotropic base boundary, you have a tetragonal plus cubic-like. If the cubic-like were rhomboidal, one can explain the entire thing in terms of the conventional mechanism. But as is shown here, the cubic is suppressed, which is not likely the case. If you are rhomboidal, apply electric field, it is not going to be suppressed completely. Some studies have shown that these cubic-like regions correspond to still tetragonal phase, but they are not long range order tetragonal phase, but very small range order tetragonal phase. So what happens that when you apply electric field, so this small range order tetragonal become long range order tetragonal domains. And when you look from the XRD point of view, which has a larger coherence length, it sees everywhere tetragonal regions because the small range which appeared as a cubic has completely gone away from the scene. Now coming to why it is showing such large electron strain. So this is a in situ XRD which we carried out in our laboratory as a function of electric field on a pellet of this composition which is showing the large electric field. As you can see, this is a tetragonal peaks and this is a cubic peak, which is basically nothing but, as the TM has shown, a small coherence length of tetragonal domain itself. So if you apply electric field, you can see the intensity reversal of these two. This intensity, this is smaller here, this is bigger here. Reverse is the case here at 60 kV per centimeter. This is a manifestation of domain switching. So this reversal is suggesting that the domains have switched. And most importantly, what is most important is that cubic-like phase. If you look at the peak position, it is moving towards the left. It is suggesting that the lattice parameter of is increasing. So this explains the whole mechanism of why this extraordinary response is. And once you reverse the field, for example, come back from here to here, it almost get back to the same situation. So it means that there is a strong coupling between these small short coherence ferroelectric tetragonal regions and a long coherence ferroelectric tetragonal regions. And their strong coupling enables this elastic recovery of the domain switching back to their original configuration. So this scenario is like a rubber where you have a restoring force. When you stretch a rubber, some alignment of the molecules happens, but when you release, rubbers come back to the initial position because there is some restoring force which pulls the molecules together and again realign in this original configuration. A similar things happens because of this small cubic amount of cubic fractions, or which is basically small region. This explains this phenomena. We not only found this phenomena in this material, but we also discovered that the same phenomena is also responsible for showing large electromechanical response in two other systems. Because of lack of time, I will not go into it. And we also, there are other facets which have explored. One facet is photolytic catalytic activity of ferroelectric material. For photocatalytic activity, we need a ferroelectric material with a band gap of, let us say, 2 electron volt. Bismuth ferrite is one such material. A study was reported in the past. We wanted to investigate if the phase coexistence has some role in manipulating the photocatalytic activity of the semiconducting material bismuth ferrite. We found it so that there was one composition is bismuth ferrite lead titanate, which for the same particle size can give two crystal structures, tetragonal and rhombohedral, just by different heat treatment. And this ensured that the particle size remain for the tetragonal and the rhombohedral the same. This is very important for photocatalytic activity. We carried out, and the band gap also remains almost same in the 2.1, 2 point regions. And we carried out photocatalytic degradation of some pollutant and determined the rate constant. And we found that the one which shows a coexistence of tetragonal plus rhombohedral ferroelectric phase has almost 4 times higher photocatalytic activity compared to the pure single phases of rhombohedral or tetragonal. So this was one, and we have also, and because of lack of time, I will not go into it, but there are some interesting results where we have tried to manipulate the photoluminescence doped inside a photoelectric material by electric field and also by temperature, and found some very, very interesting results. Because of lack of time, I will not go into this, but there are many interesting phenomena related to ferroelectricity which we can still play about. And I think this is what this makes this material, though discovered, this phenomena discovered about a century ago, but there are many related mechanisms which you can find and keeps this material interesting. Thank you very much.